So we're going to go ahead and continue. I just wanted to bring you back to this, where it says optical isomerism. Notice the examples that they want us to look at. They want us to look at 3 bidentate ligands, or 2 bidentate ligands and 2 monodentate ligands. So in the video, one of the last things he said is when we look at the optical isomers, we're either going to do it with 2 bidentate ligands or 3 bidentate ligands. You don't see it for monodentate ligands. So with that being said, let's see if we can figure this out. This is the one for 3 because he didn't show that in the video. If you have 3 bidentate ligands, I don't think it's too difficult to figure out. You put them 3 different ways, and then you just split the molecule the same way that you usually do for chirality. Let's see if we can try to write optical isomers. It says draw 3-dimensional diagrams for the 2 optical isomers of CO, NH3, 2, EN2, and how to write your EN ligand. Write it as N, the 2 lines, and another N. So what would be the first thing we want to do to prepare this? First thing that I would do is just fill in my octahedral shape to kind of get an idea of what I need to do. And this is the way that Cambridge does it, with the dashes meaning go backwards and the wedges meaning go forwards. So do that again here. All right, so we had went over the idea that the trans variant will not have an isomer. So we have to write the cis variant. So as we're figuring out what to plug in, I would start by saying, well, if I'm getting a cis variant, why don't I plug in my NH3 first? I want to make those 2 NH3s, cis2, each other. So I could put one here, and I'm going to put the other one right here. So far, so good? Now I'm going to fill in my 2 bidentate ligands. So I'm going to put N here, like that, and N. The same thing here.
They're 90 degrees, right?
Yeah, these are 90 degrees apart from each other. And then N here, and here. Next to each other is always 90 degrees apart in octahedral. Yeah, N here and N there. Because it says each ligand can be represented using this. This is EN. Yes? So far, so good? So for the optical isomer, how do we flip it? What would we do now to get the guaranteed optical isomer of it? This NH3 would be at the top, but where would this other NH3 go? Would it go on the left side or the right side now? The right side. That gives you the mirror image. And then however you wrote this, you're going to write it the same way. And then here, you write it like this. I had created these this morning just to give an idea. This is a similar, except it's with oxalate instead of EN. And so these are my 2 mirror images. This would represent my 2 mirror images. If I try to put them on top of each other, notice how the groups go out of opposite sides. So they cannot be mirror images of each other. And so, like I said, you may want to borrow or come to tutoring and practice with the model kits to help you gain a better understanding. I'm going to count how many I have to see if there's enough to do a group activity with it, but they do help you to visualize what's going on if you struggle with 3-dimensional reasoning. Are we good? Question?
Well, isn't it if you just shift the one from the left, everything up by 1 to the left, it would be the... I'm not sure how I'm explaining it right. Wouldn't it just... Yeah, okay. That's never mind.
Okay. All right. So that was one practice question. How many marks is this worth? 2 marks. So the point I want to make is this takes up a lot of space. And that's why your paper 4 is 20 pages long. It's because this 2-mark question takes half a page. It's worth 2 whole marks. So especially when you get to this component of the class and the organic component of the class, you're going to be writing big things. And so because of that, that's what extends like how many pages the case exam is. That's why paper 4 is gigantic in terms of the amount of pages. All right, so take a look at another question. It says there are 3 stereoisomers very similar to the last one that we drew. It says complete 3-dimensional diagrams to show these 3 isomers. When I was going over it last night, because I was going over the questions, I thought to myself, these 2, because they're writing them left and right to each other, I think they're trying to get you to think that those should be optical isomers to each other so that you could write the mirror image. So these 2 should be your cis, and then the one down here should be your trans. Because remember, the cis isomers are going to have the mirror image, the trans does not. So I would actually start by writing the trans though, because I think that's easiest. So how would I write the trans here? What would be the ligand that's trans here? What's the ligand that's either going to be cis or trans to each other? The C2O4 or the H2O? Nope. The mono didn't take ligand. So water. So my transvariant for water would be just like writing H2O like this, H2O like that, right? Trans. How do I plug in the C2O4? So we're not very nice here. How would you plug in the C2O4? What is C2O4? Isn't it like that? So how would you plug that in there? The oxygens are the ones connecting, right? So it would be like this. Do you agree? That's C2O4. Because when the oxygens, they bend in. I think I showed that to you earlier, but this is actually C2O4, the one that I built earlier. I built these 3 actually. I built, or something very similar to what these 3 are. This is C2O4. It's got 2 carbons and 4 oxygens. Notice that these oxygens end up being 90 degrees apart, right? So it's this is that. They're the same thing. All right, what about the other side? I got to do the same thing over again first. This is such a, and this is a newer question, by the way. This is from a recent test because I had put this last night. And then this oxygen should be going here to the line right there. That's the wedge. Should be going that. That's the transvariant, right?
I just got shot.
Now, what about the cis variants? How would I do the cis variants? 2 optical isomers for the cis variants. Instead of your water being 180 degrees apart, your water now needs to be 90 degrees apart. So how I would do it is, well, first of all, I should prepare my octahedral diagram. And I feel bad for the 2 students who are not here today. I'm just throwing that out there. This is one of those lessons. This is one of those lessons. Like if you miss one of the, like if you miss enthalpy, like that's a rough one to miss too. Like that. Oh no, that's not right. That's a crop. I need them to be next to each other. So where would I put the second water? It could be any of these 4, but I would put one of the 2 at the top just because it's easier to visualize, but it can be any of the 4. I want to make sure my bidentate groups are next to each other. So I would put my water, for example, you could put it here. If I do it that way, how would I write my bidentate groups? This would now be O.
So beautiful.
Oh, sure. And then that right there, that's one of them. And the other one would be like this. Like that. Like 90 degrees apart, right? And then we have to flip it for the other optical isomer. So in this case, instead of the water going here, this is my mirror image, and the water goes like this. And now I do the same thing. Usually they tell you can, simplify it, make it easier, but they do not say so in this question. That's why I said it was a little. The two closest here are the two closest there. So that would be it. How many marks was this one? This is worth 2 whole marks for all 3 of these correct. Yes.
Do we ever go back to double bonds, cis trans isomerism?
I mean, if they do, they're assessing you on an AS chemistry standard. Yes.
Okay, so can you is there any way to simplify not writing the double O's each time and the
It depends on how they tell you to write the question. Like sometimes they'll throw you a bone and say you can just do this. Yeah, like sometimes they will. Like give you a simplified version, and then sometimes they'll tell you you can just do it like this. But then here they didn't say that, so they didn't say you should simplify it. So you can only simplify it if they tell you to, how they tell you to. Otherwise, you should be writing the whole thing. All right, now here's the last part of this question. Use your answer to C2 to answer the following question. Stereoisomers 1, 2, and 3 show 2 different types of isomerism. I already kind of guided you to this. Name these 2 types and which pairs exhibit those types. So, what are the 2 types of stereoisomerism we've been discussing? Cis trans, which is geometric, and the other one is optical. All right. What is a pair of stereoisomers that's cis trans? From this diagram. 1 and 3. But you could have also chosen 2 and 3. But 1 and 3. And then what is your only pair of optical isomers here? 1 and 2. And so how many marks was that word? 2 on this. It was part of the same question though. And I think if you don't get this, then you don't get this. There's no way for you to figure out which one if you don't get this right. All right, last topic for the day, leaving geometry. That's what all you need to know about the geometry of complexes. So the last topic for the day, I'm trying to get us a little bit ahead so we can spend more time on activities next class. And so I did last year as well. I made this lab last year, so I have to review it and revise it for this year. But you should be doing a lab on Thursday with ligand substitution. And so ligands in a complex can be exchanged either completely or somewhat for other ligands. This is called substitution. It's a type of substitution, but you must call it ligand exchange or ligand substitution. If you just say substitution, if they ask you for the type of reaction and you don't put the word ligand in there, you will not get the mark. You have to say it's a ligand exchange or a ligand substitution. And so why does it happen? Well, when we learn our last lesson of the unit, we're going to go into detail of how it happens. But for the basic variant, it's if the complex you formed is more stable than the one you originally had, then it will form. So because in chemistry, we seek stability. And so the more stable, if there's 2 different ligands, the one that's going to attach is the one that is more stable. We're going to go deeper into that in the last lesson. It has to do with equilibrium. So there will be an equilibrium constant for this, actually. It's called K-stab. So if you see any questions that have K with the letters STAB, that's called the stability constant for stable complexes. All right, so anytime you've seen, I've already brought this up. If you've seen copper 2 plus aqueous, what it actually was copper with 6 waters. And this gives copper sulfate, which is probably the one I'll be preparing for you on Thursday. It's characteristic blue color. It looks like that really pretty blue.
It's like for their shield.
And so here's, I don't know, maybe bad news. There's going to be a decent amount to memorize here. you are going to need to know for all the copper compounds, and I mentioned this at the beginning of class, and all the cobalt compounds, all the different colors they make with different ligands and their ligand substitution reactions, like how they go. So let's take a look at this one. Copper sulfate in water is initially blue. Predicted final complex is this. So now the question is, if I put concentrated hydrochloric acid in here, and yes, I will be providing you with pretty concentrated hydrochloric acid on Thursday. What does that mean? That means be extremely safe, gloves and goggles. I suggest long sleeves, no Crocs for sure. Because it is one of the more dangerous lab exercises because of the high concentration that has to be used, both for the hydrochloric acid and for the ammonia. So definitely make sure you're following safety procedure. But yeah, if you don't have a high enough concentration of the ligand, you can't get it to happen. Basically, you won't see the color change you want to see. So it has to be a pretty high concentration. And no, I'm not going to give you as high of a concentration as I could. You will not be getting 98%, but you will be getting about 6 molarity hydrochloric acid, which is way more concentrated than I usually give you. So even with that high concentration, and if you read the textbook, you'll see they've showed a picture of this. You actually don't observe the yellow color, and I apologize in advance. If this ligand substitution completely happens, the color you get is yellow. Every time I've ever done this, even with completely concentrated hydrochloric acid, I get green.
Bruh.
Why do you think that's so?
Because they're lying to us.
No.
Oh, because copper's right.
Well, if I start with blue and I'm adding the chlorine, which makes it yellow, what's the mixture of the in between? Green. So it means that the ligand substitution is not complete for every copper molecule. So you get, it's how you mix colors. And we'll be talking more about color mixing in the last lesson.
So
Yes.
so it's kind of like paints.
Yeah, in a way, with chemistry. So what do you get out of this? It's 4 chlorines, and this will always give you a tetrahedral complex. It's CuCl4 with what charge? What would be the charge now? It was 2+. I added 4 chlorines that are -1. So this is actually going to be -2 or 2 minus. But then where'd the waters go? You're supposed to write that they get kicked out. They got kicked out. That's a substitution. Chlorine in, water out. Swap. For NH3, and I was looking at the notes in the textbook last night, and I think they just expect you to know this, that when NH3 does a substitution, it substitutes specifically for it. That's why I said it's bad news. All of this pretty much has to be memorized. It substitutes for, so you end up with this. Cu, NH3, 4, H2O, 2, 2+. And where did the other waters go? They get kicked out. So if I was to complete the reaction, I write this, plus 4 waters, right? And then with hydroxide, you get not a ligand substitution. This is not a ligand substitution. You get something instead called a precipitation, meaning that in these other cases, you're not getting a solid solution, like there's no solid at the bottom, but in this case, you get copper hydroxide, which is a PPT. Just CuOH2 solid. And then the waters get kicked, still get kicked out. But this isn't behaving as a ligand, it's behaving as a regular ionic compound in solid phase. You'll see it when you do the reaction. And you may or may not remember when we did qualitative analysis last year. When we did add ammonia, it started off with like a pale blue PPT before it got to deep blue. And you had to keep adding excess ammonia to get to the deep blue. So you actually saw it on the way to getting to ammonia. So one of the things I think is really weird about the AS class is they give you ammonia to do qualitative analysis with when you haven't learned about ligand substitution yet, so you don't know why the colors are what they are. So they just give you a chart in the back that says, here's the notes, here's the reference notes to go with. Because technically, if you had more practice with it after you learn this content, it would make it easier to understand, oh, that's why that turns deep blue when I add ammonia, because it's a ligand substitution that does that. And you'll learn about why the colors change in the last lesson for the unit. Like, why do these color changes happen? That's a whole discussion of wavelengths and frequency, those topics. Light being absorbed versus light being reflected. All right, so we have to do that for copper, but we also have to do it for cobalt. So for cobalt, it's very similar. Key difference is instead of 4 NH3s, it's 6 NH3s. That's one of the key differences that I have. And then from there, it's going to be, this is cobalt, H2O 6. And it starts off as pink. Then if I add chlorine to that, it turns, instead of pink, it turns blue. Last year, we did not get the second result. Not sure if we heated it up enough or not. I saw a note in the textbook that if you mix this with NaOH, you get blue. But apparently, if you can heat it and your alkali is in excess, you should get red. Last year, when we tested that, we didn't get it. But you can test it on Thursday and see if you get it. Supposedly that happens. But you'll definitely get the blue from the first part. And so this would be CO, OH,
And these are
Two.
coordinate shields.
and then this would be with the 2+ charge, and then plus 6H2O.
Wait, Miss, how come it's 2 for OH? Doesn't it have a coordination number of 6?
Or, sorry, this is 3. What?
Does it OH have a coordination number of 6?
Not in this case. It's specifically these amounts. And that is why this unit is so much fun. For these cobalt and copper complexes, you have to remember that these are the exact ligand substitutions that go on. And then finally with NH3, a key difference is instead of 4, you get 6. So this would be CO, NH3, 6, 2 plus 6 waters. All right, and then those are the colors. Pink, blue, blue, and brown. Probably yucky brown. And I think we've gotten yucky brown in some of our labs before. So we'll get to see these colors in action on Thursday, or many of them. You won't get yellow though. I'm telling you, it's gonna look green. You're supposed, but on a Cambridge exam, you don't put green. You write yellow because you have to write like as it's completed. So that's unfortunate, but it is the way it is what it is. Okay, so let's take a look at these types of questions. This is actually our last 2 slides. I think we did it. So that means we're going to be able to do mainly activities on Thursday. That's awesome. So I'll put that together. These are our last 2 slides so we can see how these questions are oriented. I just want to point your attention to how many points this is worth.
Even more than the other.
No, the stereoisomers was like worth 2 for like a whole page of work. And then this is worth 6 for like,
Colors.
yeah. Point distribution is crazy. All right, so let's see. Samples of copper are reacted separately with sodium hydroxide or with aqueous ammonia. Reaction 1, give the color and state of the copper containing species when you react this with sodium hydroxide. So what's that? It's on the charts. Copper with hydroxide. It's pale blue PPT. So if you wrote, I believe in the mark scheme, they accepted just blue PPT. Let me double check. Yeah, they accepted just blue PPT. Blue PPT. And are you allowed to write PPT instead of precipitate?
Yes.
Absolutely. Why write more than you can write less? Ionic equation. Oh boy, what's that? Remember that thing? They're asking for the chemical reaction here. What am I reacting this with?
Next
The-
step is 100.
Sodium hydroxide. Do I include the sodium in the ionic equation? No. Do you have to pull out of your head that it's two hydroxides? Yes. That's why I said it's kind of a gross slide because you have to just know that it's going to be two hydroxides. And so then what do you make from that? You get copper hydroxide, CuOH2, plus 6 water. Now, here's the track. What type of reaction is this? It's not a ligand substitution. This is the one that I wrote here. Not a ligand substitution. What is it?
Precipitation?
It's precipitation. If you make PPT, that's your clue. You can just write precipitation.
Precipitation is a type of reaction.
I mean, it is part of double replacement. So you would have written it as a double replacement. But the thing is that you don't see the double replacement because you're not writing the sodium. So they call it precipitation because you make it. Reaction 2, ammonia. What's the color and state of what you make from that? No, it's ammonia. If it was chlorine, it'd be yellow. But it's ammonia, so it's dark blue. What's the state? Dark blue solution. If you say liquid, you're saying it's like one thing, that's not a mixture. You gotta say it's a solution. Ionic equation. Start with the copper again. Do they expect you to know how many NH3s are going to react off the top of your head? Yeah, they didn't provide that information for you, so you have to know that it's 4. And are you understanding why this lesson is not going to be on your quarterly next week?
Yeah.
Like why I stopped it at the one before break because it's too much. Like I'd rather you focus on this afterwards, after the quarterly. Okay, so now what do we get from this?
Cu, NH3, 6.
Not 6. 4. And then 2 plus, and then you pick out. Technically, if you look at it here, it's got 2 waters as well. You have to remember that. Yeah, that this has 2 waters. And then you kick out 4 waters. Type of reaction here. This is called a ligand substitution. Could you get away with writing ligand substitution for every type of reaction and hoping for the best? You pull a mark or 2 out of that if you're unsure. And you know it's transition metals and they're like type of reaction. 5 out of 6 times you're going to be correct with ligand substitution. So usually ligand substitution. What? That's going to be you? All right. Ligand exchange, ligand substitution, either is fine. Last section. Same type of question. This is a more recent one. In a more recent exam, but very similar. It says write an equation and state an observation that can be made immediately after the reaction. So now this is with cobalt. So what would we get from cobalt? Cobalt, H2O6, 2 plus. What happens with the OH minus? How many OH minuses always for these? 2. For OH minus, you get, in both of them, it's 2. There's only one that's different, it's the ammonia. So for this, it's 2. And you're making cobalt hydroxide.
Yeah, that's what I
And what is the color of cobalt hydroxide? It's blue PPT. 1 mark for the equation, 1 mark for the color. Yes.
Oh.
I would not include the spectator ion, and the mark scheme does not either. So I would not. I think I would just get more confused. Most people would get more confused by including the spectator ion. So it's a good point. Make sure you're only caring about the ion that's reacting, not the spectator. We're excluding spectators here. Here they don't include the spectator, here they do include the spectator, but you don't include the spectator in your answer. So, NH3. What's this one? How many NH3s for cobalt? That's the copper amount. NH3 is the only one that's different for them. It's 6. So it's 6 NH3s. And then you get CO, NH3, 6. 2 plus 6 H2O. What's the color? What did they say? They said it was brown, right? Brown. You want to know what the mark scheme accepts? I'm going to tell you everything they accept. So they accept brown, but the other colors they accept here are yellow,
Of course.
but they wouldn't accept green for copper chlorine. They accept yellow, and they accept straw.
Oh.
I think that's a British thing. They accept the straw, like like I guess like hay, like the color of hay. I think is where that's coming from. Something where they can think. Put the straw solution. That means people write that.
Yeah.
If they put that in the mark scheme, that means people write that as a response somewhere. All right, last one. How many NH3s for cobalt? Or how many NaCl's for cobalt? 4. And would I include the sodium? No. So it's 4 Cl minus. So CO, Cl4, 2 minus, plus 6 waters. Observation. What do you get here? This is just a lithium. Closed solution. You do not have to say that it's red on heating. You do not have to say that. And like I told you, I saw it. I read it in the textbook, but we weren't able to do it last year. But it's not in the mark scheme either. So, and then name the type of reaction that occurs in this last part. What is this type of reaction? What is this? Ligand substitution or ligand. You don't have to say substitution. You can also say exchange. It's up to you. Ligand substitution or ligand exchange. All right. So like I said, that's a bit of a doozy. It's a lot of information. The other thing I wanted to point out before we go for the day is notice how in some of these reactions, the geometry is changing. And in some of these reactions, the geometry is not changing. When you make the chlorine, that actually changes your geometry from octahedral to tetrahedral. Here, you are going from octahedral, and it's still octahedral. Here, you're going and not even getting a ligand substitution at all. So also take care of that because they could ask you about the geometry changes. All right, we did it. So we got through lesson 5. There's technically only one more lesson left for the school, unit. But we're not going to do it yet. We're going to have a lab next class and an activity. Then we're going to have next week your quarterly. And then after that, we'll take a look at when the last lesson is. So study up for the quarterly. The homework for this is going to be due next Wednesday on the day that's not the quarterly. But get started as early as you can because it is a lot of information.
Last lesson. I did make